All right, welcome back to System Software. Today we are right in the middle of processes. And we're going to go over, so the last couple of lectures, we looked at what processes are, the abstraction, looked at how to work with them with the shell, which can be useful in practice for just operating your machine. But today we're going to start actually learning how to program with the kernel's API. But before I begin, questions about last week, questions about the project, questions about anything. Logistics, the FS project, homework. Well, I'll go over homework. But. Yeah.
For the project, you mentioned to exit precedents, but you also said to any other exit codes to just do exit failure.
Yeah.
So after 4 and 5, when you want to just do exit failure, because I just kept pulling a number.
Yeah. You can just use exit failure. Yeah.
After 4 and 5.
Yeah. Yeah.
Exit precedents.
Oh, I see what you mean. Yeah, that's a good point. Only the lowest number of exit codes should be produced. Well, yeah, that would still fit, right? For any other syscall error, it would be exit failure is the lowest. It'll be 1 on the system. So I'll, that's. Yeah, that's fine. Yeah, that's right. I'll clarify this. Hopefully that'll be clearer. Other questions on FS? Other projects? It should be. It's not updating. All right, let's go over the homework. All right, what's a process? Oh, sorry, was there another question? Did I miss one? Okay. Yeah.
So just to make sure, if I got this exit 5, is that fine or not?
Oh, you mean you added additional exit codes?
Yeah.
Just use exit failure.
Okay.
So for this one, so for any other system calls that fail, use exit failure. Yeah. Sorry, I think I didn't understand your question. But yeah, use exit failure for other failures. And if there's something not listed here, I'm not going to test it, basically. If it's not in the specification, I won't test it and expect a specific error code. So you could add your own exit codes, but for other cases, as described here, for a bonus project or something. All right, what's a process? Yeah, running program. Good. Okay. Yeah, it's repetition to get you. So it's in your mind what a process is. So when we get to OS, you'll be ahead of the game. Okay, so this is a question about using the shell, which I hope that was clear. How do I send the output of a find command to the input of grep without having to create my own file explicitly? What's that? With a pipe. Yeah, that's right. And okay. Right, so if I say find here, I'll get a list of the files, and I use the pipe symbol, which in Bash, and I think most of the shells, is this vertical bar, usually above your enter key on a US keyboard. And then I can put pivot to the grep command. So what it does is, how does pipe work? What does pipe do? Semantically or conceptually? Right, yeah, it redirects or pipes the output of the first command to the input of the second command. And how does pipe know which input and output to use? We didn't specify which part of the output. How do we? Yeah.
Left, right, but you can also redirect the errors
Right, you can redirect errors, so I could say like find redirect errors. But how does this know, how does Bash know which, so you can have many open, you can have many I/O, much I/O in your program. You can open as many files as you want. How does pipe know which one to use? What's that?
Just using standard.
That's right, yeah, it uses standard I/O. So it always uses the standard out for the left-hand one and uses standard in for the right-hand program. So this works because we have standard I/O, and each program was written, each of these programs, find and grep, was written to use that standard I/O convention for its input and output. Questions on that? Standard I/O bit? Or the piping? Okay. Let's see if you remember this. How can I run a program as a background process in Bash? And there are multiple ways of this, yeah. Yeah, you can use ampersand. So I can say sleep for 20 seconds. Oh, can that work in the background? And now there's this program, sleep. Oh, okay. I also have Emacs process running in the background. So using ampersand will immediately make it a background process. And this is just in Bash. It just means that Bash's standard I/O will no longer be, it's the terminal I/O will no longer be connected to this program. And I can resume it with FG for foreground. What's the other way, or what's one other way? What's that? Yeah, that's true. Yeah, so you could run a TMUX, which is a terminal multiplexer. I didn't really cover this last time, but yeah, that would be one way to put it in the background, because you can just detach from your TMUX session or switch windows. What was the other way I talked about last time? Did someone say it? So you can use Control-Z. Control-Z will take a program that's in the foreground that is connected to your terminal in I/O, hit Control-Z, that will pause it, and then BG for background. So these are useful, especially if you're doing any IT or computer operations or development at the systems level. It's useful to know how to manage the processes on your machine. And the workflow that I showed you on Eustace, the convenient workflow to avoid having to reopen a file all the time, was when you're in Emacs and editing, hit Control-Z. So you can't see the key command I'm hitting, but I hold Control, hit Z, and you can see it tells me that this process has been stopped. I can run jobs to see that it's indeed stopped. I can run process to see that I've got this Emacs process running. Then I can do my development and compilation on the command line. I call it hello.exe. And FG to resume that process in the foreground of Bash. Questions on that? Just a useful workflow. Should make you a little faster on Eustace. And yeah, that was the answer to 4. I didn't even look at this. So that's how you do it. You can pause it with Control-Z. Yeah.
So if you have two programs in the background, how do you choose which one again?
Oh yeah, that's a good question. So I can let's say I'm editing Emacs. And then even though Emacs can open up multiple programs myself, I could have, let me make a different program. Let me sleep for 100 seconds and put that in the background. So when you run jobs, it'll number the processes, and then FG takes an argument.
Oh, okay.
So yeah, I can do FG1 to specifically get Emacs, and FG2 to specifically get the sleep program. And it conveniently tells you, what program you've resumed. And BG to put in the background. Same with BG. I can say BG2. Yeah.
I have also. If you will leave your session, your
Yeah.
shell session, does it stop every single background job?
I think by default it does. I think it sends a signal to each of these. You're kind of stretching my knowledge of this. But you can... So the way you used to have to do this is there was a tool called no hang up. So basically when you quit, I think what happens, if I'm remembering right, is every process gets sent a signal to say, hey, this person left their shell. You can do what you want, but by default I think they'll hang up, they'll quit. If I'm remembering right, I can't remember it exactly, but you can. Is that right? Actually, maybe that's not the case anymore. You can. They shouldn't quit. They shouldn't quit. You should be able to leave stuff in the background. Because nowadays I just use a terminal multiplexer to do this. But Eustace is configured to prohibit any background processes that are left after you quit by their config file. I can't remember what it's called. There's like a setting to do this. But normally you would be able to leave processes in the background. I can't remember if you can just leave them in the background and then quit, if that'll quit them, or that'll just like work if you do that. But there's a setting that does this. I don't remember which it is. I can't remember which it is. But yes, you can, on your own machine, if you have it configured properly, you can leave processes running in the background after you quit. And nowadays, I just use a terminal multiplexer to do this, which manages it for me. So I don't remember the mechanics of how it actually works. Yeah, I can't remember what setting it is. Anyway, something Googleable. Ask on EdStem if you want to learn more about this. I'll send you resources about it. Okay. Other questions about the homework? All right. So there's this Stack Overflow post about the multiple ways to keep a process running if your server is configured to allow it. So NoHup was one. There's apparently something called disown, which I had never heard of. Disown will, I guess, change the ownership of it, and then what I typically use now is screen. Where was this one? Tmux or screen. Anyway, so if you're interested in doing any, logging into any servers and doing more than what we're doing in this class, I can use those tools for that. Okay, let's go into our. Any questions before we move on to today's lecture? All right, so let's look at how we actually work with processes programmatically. So recall that the way process creation works is there's two steps to create a new running program, a different running program. The first was forking. And what does fork do? If you remember from last time, what does fork do? Yeah. It duplicates the process, like this, I don't remember the term for this, what is meiosis or something? One of these biological terms. It's like that. You kind of create a clone of your process, and then if you want that process to be a different running program or replace it, then you use the exec system call. So doing this kind of gives you very fine-grained flexibility over processes. You don't always have to run a new program. You could do parallel processing with a single program if you want. So that's the workflow. So who read the Linux Programming Interface book, the chapter 24? Okay, so somebody read it. All right. So if you read that, then you'll see this diagram, which visually shows how this process works. So we've got our parent process. So some process is already running. Then we call fork, and now have two processes. We've got the parent process, and we have the child process. And they're duplicates of each other, which is program A. So if this is program A that's running, so program A is running again, and it's running from the exact same location as the original program. All the memory has been copied, the stack, open files, all of that is duplicated. So they are clones. They are doing the exact same computation at this point. But if in the child process we call exec instead of just continuing on with the program, then now we'll have the running program be. So what exec does is it takes whatever program you specified, because remember, a program is just a set of instructions, might be on disk, it's not running, and it replaces the memory of the current process. So let's say I didn't call fork. Let's say I called exec here instead. What would happen? Would I have a new process? No, there'd be no new process. And what program would be running if I called exec B here instead? Yeah, it would be program B, or yeah, it would be that program. So calling exec by itself does not create a new process. It just blows away your existing processes running program. And then wait is another syscall which will basically block, it'll stop until the child process or a child process has terminated, and then wait will continue after waiting. We won't do too much with wait. I'll probably just give you the code for this. Once we get to bash, yeah, we're only going to have one process by default. But if you're using like the bonus project, you might have to do something more sophisticated with waiting. This is in your, the textbook that is provided to you for free by UCF, the Linux Programming Interface. So this is there in the textbook. Questions about this process? Yeah.
So if we run fork, will program, so let's say the child is looking at the parent. If we run fork, will the parent keep running or will it stop?
It'll keep running. Yeah, they'll both, so it'll be like, yeah, you have the same running program running twice. They'll both be running, yeah.
So the parent and child will both run then at the same time, but if you run exec, then the parent stop running, is that what you're saying?
No, the parent continues running as well. So this may seem a little counterintuitive. How is it possible? So if they're really the exact same program, how is it possible that one will call exec and what the other doesn't, right? Because it's the same program. You write the same C program, the same sequential list of instructions, and how can one process run exec? So let me, so this is the next question, the slides. This is what happens with fork. Fork duplicates the process. The exact same program is still running, same open files. The memory is conceptually it's copied. So then the question is, how do we just avoid the process just always doing the same thing? How can we make one do exec or one do something different? And the trick is that there's one little difference, and not in the process itself, but there's a difference in what the kernel does for the fork call. So when fork is called, after fork is called, there are two processes that are identical. But what the kernel does is it gives a different return value to the parent and the child process. And that's, from the programmer point of view, that is the only visible difference that you have. But because that is different in the parent and the child, we can use that. We can make a test for that value to see whether we're in the child and the parent, and then we can write different code in an if branch for both the parent and the child. So just like you learned in C coding, you use an if statement if you want to have the program take a different sequence of instructions depending on some program value, depending on some input value or program value. And it's the same thing here. So we have one program, but there are conditionals in it that allow the program to take different paths in the program. And the kernel will pass return a different value from fork for each of them. Questions on this? Does this sort of make sense? Okay, let's see an example of this. So let me just copy this code. Or I think I have it already. What did I call this? Simple fork. Okay, so here's my first use of fork. Let's take a look at the man page. So this is the best way to get information about this. So this is the description of the return value for fork. So on success, the PID, the process ID of the child process, is returned in the parent process, and 0 is returned in the child. On failure, -1 is returned in the parent, no child process is created, and error no is set to indicate the error. So what's the process ID? Remember what the process ID is? If you type the PS command, you can see the process ID. It's just a unique number that the kernel assigns to each process that gets created in the system. So you can see that whenever you type the PS command to see the processes. So this is how we'll distinguish in writing a single program. This is how we'll be able to tell the difference between a parent and a child. So here I've written a program that just does the standard error checking, where we only check if it's an error where the kernel couldn't fork a process. So you've run out of your quota of processes, or you ran out of memory, which is maybe possible on embedded systems. Okay. So a little kind of quiz. What will happen if? Oh, that made people perk up. It's not a real quiz. Don't worry, it's not graded. So what's going to happen with this program? If I run this program, what should I expect to see? So let me build it. And when I run this, what should I expect to see? Let me take out these sleeps, because I don't feel like waiting for them. What should we see? What would you expect to see? So if I didn't have this fork in here, what would we see? We see hello world. With this fork, what should we see? 2 hello worlds. Yeah, good. We should see 2 hello worlds, because this is showing, forget about the exec part, but when we see fork, at the point of this call to fork, after it returns, so this is the man page for fork, on success, the PID of the child process is returned to the parent, and 0 is returned to the child. So if fork is successful, there'll be 2 processes running the exact same code at the exact same point in the program. So once we get to, as long as it's not -1, the next point in the program is here. And we have 2 processes running the same code, so we should see 2 hello worlds being printed out. And let's see if indeed that's what we get. And indeed we get 2 hello worlds. Isn't that amazing? Is that not amazing? Okay. So why are they both printed to bash? What's that? Well, okay, where else do they print it? So if we don't have fork here, why does it get printed to bash? Why does printf? So we didn't say where to do printf. Where's this process? Where's printf going? Standard out. Yeah, good. Standard out. And so why are both processes going to standard out? Or bashes out? Yeah. Exactly. So when this fork happens, not only is the running program, the memory, but any open file descriptors, so any open files. So this is a diagram also from the Linux Programming Interface textbook. You can see here that this is before fork. We've got 2 open files. Let's say it's standard out and standard in. This is the table in the kernel that keeps track of these open files. And then when we call fork, the child process has a new table for its open files, and they're duplicated between the parent and the child. And you can see that both the parent and the child point to the same open file. So if this is standard out, then both the original standard out, the original process standard out, which is bash's output, which is the terminal, then both the parent and the child are going to have, both as standard out, they're going to have bash's output as the open file. Does that make sense to everyone? Remember, files are not just your documents on disk. They're I/O. They're I/O ports, in a sense. Questions on this? Questions on why this happens? Why when we run this program we get 2 hello worlds? Yeah.
Yeah. Can you explain again why it doesn't fork infinitely?
So so at this point in the program here, we have one process running, so by bash, right? And even, let me do it this way. So let me do it in a way that's less sort of C-like here. Oops. All right, so here we've got one process, and as long as ret val is not -1, as long as the kernel didn't throw an error, then right now we have two processes already.
Okay.
Here we have two processes.
Oh, so they both, the second process doesn't start from the beginning?
No, exactly right. Yes, you're right. It doesn't start from the beginning. And that's because what it does is it saves the state of the processor as well. That's what the process contains, the state of the processor. And one of the registers, remember from computer organization, is the program counter. So that program, so if you looked at this in like a machine code, which we'll look at this, we'll look at machine code later. But you can think of this as like line numbers. So this is line 1, and this is line 2. And that line number is kept as state in the processor for the machine code state. So that state is also copied for the child process. And so once fork has returned, the next line for the process is line 2, and so both processes are at line 2. Yeah, that's an important distinction.
Yeah, and then the only distinction between them is what gets returned by fork.
Exactly. So there are two processes, but ret val for one will be 0 for the child process. Ret val will be 0, and for the parent, ret val will be the PID of the child process. That'll be assigned by the kernel, as long as there isn't an error. But yeah, that's a good question, a good distinction. So exec will start from the beginning of the program. Fork will not. It will just copy whatever the state is. That state includes the program counter or the instruction pointer, the place in the position in the running program. Yeah.
What could be an error with fork?
What could be an error? That's a good question. So let's take a look at the man page and see what errors we have. Okay, system imposed limit on the number of threads was encountered. So this is if you have a quota or a limit on the number of possible processes. So this is something that would help reduce the impact of a fork bomb. Let's see. Okay, so I don't know what this is, some scheduling policy. Failed to allocate necessary kernel structure. So this is if you run out of memory, no mem. Fork is not supported on this platform. Okay, that's a pretty obscure one. So if you have no memory management unit, MMU, this is more architecture and systems. You might just not have fork implemented. You might not have a multi-process system. And then, the classic one, the system call was interrupted by a process. So you might just have to restart. So technically you should, if you want to do like error recovery, you would actually check this and maybe restart, try to do a fork again, look at the cause. But for this class, we're just going to crash. We're just going to exit, not crash, but exit whenever these syscalls don't work. That's a good question. Does that answer your question? Other questions on fork? Yeah.
You have PID defined in a couple of functions. Does fork?
Oh, yeah.
Does that have to do with fork? Whatever you call it?
That's the return value of fork, actually. That's the return value of fork. Sorry about that. Yeah, I should have just done, so you can see it's, I kind of was sloppy and I used an int, which PID probably is of some sort of int type. But yeah, this is the return type of fork is a PID type. So I probably should have written it this way to be more correct. But yeah, that's the PID. Okay, we can actually. Oh yeah, go ahead.
So in this code, the PID was getting stored. Is the PID of the thread?
It's both. So actually, let me actually print out the PID. This is a good question. So let's print out. I guess integer should work. So let's print out the PID. So what should this program? This looks confusing. What do you expect this program to do? So we know we have two hello worlds. How many times will my PID be printed out? Good, twice. Twice. My PID will be printed out. And what will be the value of PID? Yeah, it'll be 0 on one line, and it'll be some process ID on the other line. Remember, the process ID is this just unique number given, like files have their unique numbers, the inode number. This is the process ID that you can see listed in the process table. So we expect to see two my PID lines. There's the two my PID lines and two hello world lines. And that is the difference between these two processes. That's the only difference, that observable difference between these processes, is that after fork is called, we have two processes running, but the PID, that is what's returned by fork, will be different between the two. Yeah?
So, if that child process creates another child process,
Yeah.
both of their PIDs would be 0. So how can you tell which one is the parent and which is the child?
Okay, so so you're saying if we have another call to fork.
Yeah, so after the first fork, we say if PID equals 0, fork again.
Uh-huh.
How can you tell? Because the second child will be 0, and the first child will keep its 0 process. So they're both 0.
So let me lay out the scenario. So here's my hello process running. We call, or that's not a good way to do it. Let me just say hello is running, and then we call fork, and we have one in the child. So this is hello continuing on. In the child, we call fork again. That's running. That's running. So in this call to fork, one process gets the child PID. So let's say it's PID 10, and the other one gets 0. And here, let's say the parent process, the new parent process, gets a new PID, and the child gets 0. So I don't know. Does that make sense? Does that make sense? Let me write the code. Let me write the code. So if we call fork again here, then we just need another variable to hold it. So you're saying, yeah, we could do this. You can overwrite it. This is like a C programming thing. We could overwrite it like this. But you said if you say in the child, right? So if PID does not equal 0, then fork again, right?
No, it does.
If it does, we're in the parent. So this is, we are in the parent. So if I have the child fork, it actually doesn't really matter, but this is we are in the child.
I was understood. I thought that the child process PID was 0, not that it just doesn't know its own PID.
Sorry. You're right. The child, I confused myself. Sorry, you're right. 0 is the child process. Yeah, 0 is the child process. 0 is the child process. Yeah. So this is what you're asking, right? This scenario. All right. What should we expect to happen? How many times should hello world be printed out? So we called fork, and then we only called fork in the child. So that's supposed to be this scenario, where we only called fork in the child. What should we expect to see? How many times will hello world be printed out? 3 times, right? 3 times. So you can see 3 times it's being printed out. And that's just because we just overwrite. Yeah, if you want to save the PID, then you can just use a different PID here. I could have a different PID, and then I'll be able to print out all of them. So I'll be able to save all of them, if that makes sense. Yeah.
So at what point is PID becoming equal to -1?
This is if the kernel encountered an error. So this is when we showed this man page here and looked at the errors. So if the kernel has an error, can't create a new process, then PID will be -1, and there'll only be one process. It won't create a new process.
Okay, so the child is not going to do any forking then? because.
No. The after fork. So remember, the child and the parent both resume after the fork. So let me. Okay, I've complicated this because I'm answering different questions, but let's take out the child question, the subchild question. We can look at that later when if we want to do multiple forks. But in this program, it looks like this diagram, where we have one running program. We call fork. There's one process here. We call fork, and if the kernel is successful, that is, it doesn't throw an error, then we've got two processes that both resume here on line 2. That make sense? Actually, really, they resume here to assign PID, but they resume effectively on line 2. But if it is an error, then two processes will not be, another process won't be created. There'll be one process, and PID will be -1. So just like with opening files or any other syscall, you can not check it and let the program continue, but it's not going to do what you expect. So if you want to run exec in the child, PID is not going to be 0, so it's not going to run. Yeah.
So does it try to run them simultaneously or one after the other?
Simultaneously. So yeah.
So like if you, after Hello World, if you just put an infinite loop that does like nothing, will it ever get to the second Hello World?
No. If it's only in the child. It's only in the child.
Or like, like if you just like after printf Hello World, if you put while true, like what will it print?
After printf hello world here.
Yeah.
Oh yeah. Okay.
The compiler doesn't optimize that out.
No, it shouldn't. It can't because it has to loop forever. So what he's asking is, what if neither process quits? Right? They never end.
In C, an infinite loop that doesn't do I/O is undefined behavior. So the compiler
Oh, okay.
doesn't optimize that.
Oh, okay. A while loop that doesn't do anything. You're saying?
If it doesn't do I/O and it never terminates, then it's undefined behavior.
Okay, so I could like write to a file or something to avoid that, but it's not optimizing it away. So you can see here it both printed out hello world, and both are now just looping infinitely. They're looping infinitely. So I can put these in the background, and you can see both processes are still running.
But it did get to the second one, so they are running simultaneously.
They're running simultaneously. Yeah, they're running concurrently. Yeah, this is the kernel managing this. The kernel managed them running concurrently. Yeah. Did you?
I think, even if you change it where we would like check the PID, right, it's here, like, if we're in the child process, like, both of them is the
Yes, that's right. So I'll show that example now as well. But so there was another question here. Yeah.
So if we did like a scanf on both of them, which scanf gets left first?
So the kernel can decide which one to schedule first. So I don't think there's any guarantee about which one is going to run first.
Or I think I'm better confused. Here's the system waiting for the user to input something, or will the second child process still run?
Oh, you mean if two processes are waiting for input on the same file?
Sure.
I think whichever gets there first. So they both have open file descriptors for the input, and one's going to read a little bit and stop, and it runs the risk of being rescheduled. Another process being scheduled.
Oh, and one more question. What about like race conditions, like for different variables?
Well, once the two processes created, they're both separate processes that have their own copies of all data.
Okay.
So they're not sharing memory anymore. Not to the programmer. So yeah, there's no shared memory between them in the processes. They're as if they're two separate running processes, like you ran the program twice.
Yeah, like two separate variables.
Yeah.
What about like
Same thing. They have their own memory allocation after that point. Now, under the hood, the kernel will do some optimization to avoid literally copying all the data. But once you try to write that data, it will make a copy. It's called copy on write. This is also in the book, if you want to see description of how that works. But yes, these are now two separate processes. They're isolated. They have their own memory. All variables that were in the previous process are effectively conceptually copied to the other process, and they cannot touch each other's memory. Yeah.
So if you don't scan it when you program and import it, the input that you put in will get to both programs, right?
I think it'll only get to one at a time. So whoever gets scheduled first will get to that input. But you only the process doesn't, remember we did the read call. When we did the read call, we had to specify how many bytes to read. So it's not going to read infinitely. It's going to read a fixed number of bytes as defined by the C library. And then it'll have to continue. The read command the read syscall will exit. It'll return. And then the kernel may schedule a different process the next time you try to call read. So they'll read from the same input, but they'll, with only one will get some of the data, and then there might be some rescheduling. The other might get some of the data, if that makes sense. Yeah.
How does it copy over the pointers?
Oh, that's a good question, because the pointer addresses might be different. I think it just uses the same addresses for everything. I'm pretty sure that's what it does. I don't actually know. I've never implemented it, but I'm pretty sure it just copies over the same addresses as well. So a pointer is just an address. So as long as you have the same address of the thing being pointed to, then you just copy the data over and it'll work.
Okay, so when in one process you use that pointer to change something, it won't change in the other process.
Right? No, it won't. Well, and so we're not going to cover in this class, take an OS class, but this has to do with virtual memory, because the address that you see as the developer is not the actual address of the physical RAM. The kernel is also abstracting away a memory for you. It's called virtual memory, and it can give you even more than the physical RAM you have. So you can allocate 10 gigs of memory even though you only have a 1 gig RAM chip. And so it translates the virtual address to the physical address behind the scenes for you. So yeah, you can have the same addresses in both processes, even though they might be at different physical memory locations. I don't know if that helps. But okay, yeah. OS class will go into how that actually works, the architectural support you have for that in a lot of machines. All right, these are really good questions, very, very incisive questions. And we've only looked at just fork, with the same program. All right, so let's look at so let me clean this code up a little bit. Let's leave that in there. Let's leave the PID in there. Actually, let's do it this. Actually, I think I have a version of this that's. Yeah, let's do this one. Let's do fork.c. I have a pre-created program. Okay, so this is a little bit of a cleaner one. This is one where there's a common pattern where you call fork, and then the Linux programming interface uses this. It uses a switch case instead of an if statement. But this cleanly divides up the cases of fork. So if there's an error, we exit. Case 0 is if we're in the child. Then we do have different code for when we're in the child. And when we're in the parent, we have different code for when we're in the parent. Questions on this? So just, instead of doing the same thing after fork, this program does different things depending on the return value of fork. So if fork is 0, it will say this. If fork is non-zero and non-negative 1, then it will do this. All right, let me build this program. Okay, so what should be printed out? As long as fork doesn't have an error, what do you think will be printed out by this program? Yeah, it'll print out both these lines. It'll print out inside child process, and it'll also print out this child PID line. Okay, so there we see child PID and inside child process. So I put sleeps here, so you can see that we've got, so this is the name of my program, fork. And you can see there are 2 processes running. And this was the parent, so the parent knows what the child PID is. And this is printed out by the child inside parent process. Questions on this? Does this make a little more sense after looking at fork? I hope. Yeah.
The return value of PID in the parent process would be the child.
The child's PID, yeah. Yeah, so the child process, I was mixing this up before in my code, but the child process doesn't need to know its own PID because there's a system call for getting your own PID. The parent, if it didn't know what the PID was, it would effectively lose it, or maybe there'd be some syscall to recover all of its children, but it would lose which PID that was, at least directly. So the parent gets the PID, so then it can wait for it, it can communicate with it, can do other things to that child process. Questions on this? Questions on this fork command? Yeah.
It's running both statements because the two separate programs have different PIDs, right? And one program is the parent PID.
Yeah, exactly, yeah. So even though this is looks like a single program, if we were to run this without fork, instead we would read something from the user, like have the user tell us the PID, then every execution of this program would only print one line. So if this was instead in scanf, and it would only print one of these blocks here. But the reason both blocks are being printed is because there's really it's as if you're running running the program twice with two different inputs. So this is a single program that's sequential, so only a single branch will be taken in this program when executed, but fork creates two copies of this running program, or ensures that it creates another copy of this running program, so there are then two copies of the running program. That's why we have fork running twice here. So I can illustrate that I can sleep here before we call fork, and you can see, let me resume, you can see that when I call fork, if I pause right away, I hit Control-Z to pause, there's only a single fork process running right now. So we're in the sleep call here. If I resume, then you can see that we have two processes running. You can see that process ID ending in 29 is still running here, but now we have a new process ending in 63. Yeah.
I tried the pointer thing. Like I just created an integer, a pointer to an integer, and then I set it to 0 initially, and then I printed out the value of the integer with the PID, and I changed it to 1, and I printed it out again, and it just printed out like from the original one. From the original one, it printed out 0 and then 1, and then from the child, it printed out 0 and then 1. So I guess they have different, I guess the pointers are different, kind of, because if they were the same, I'd expect it to have changed for the child.
You mean so it printed out the same value for the thing being pointed at?
It printed out 0 and then 1, and then as a child, it printed out 0 and then 1.
That's the same, right? It's the same values.
Yeah, I was just saying if they were pointing the same values, you'd expect like 0, 1, and then 1, 1.
So I guess remember that the address, the address, it's like they're both going to be having the same address that it's pointing to, but two processes can have the same address.
Yeah, but if they were the same, then wouldn't it have overwritten it for the child one?
Not if you mean only if you did it before the fork call. If you did it after the fork call, then the two processes will not overwrite each other's data.
Oh, okay.
Yeah, after the fork call, they have their own address space. So in the same way that if you run your own program, you're not actually affecting the memory of other programs. So once you call fork, they have isolated address spaces, and through the magic of virtual memory, they can even have the same addresses in that process and write those, and they won't touch each other's memory. So it's as if like each program is given its own machine with its own RAM, its own CPU. That's what the kernel provides. That's the idealization it provides, the kind of abstraction it provides. It provides for the programmer, it gives the illusion that you have your own exclusive access to RAM and your own exclusive access to the processor. So once you call fork, it's kind of like forking the machine. It's like you have two machines now, and they each have their own RAM, and they won't touch each other. But that's apparently not what? The address itself?
Yeah.
You can use printf X, so you put it in hex, and then just whatever the pointer is. But yeah, that's a good question. Yeah, try it. You can put it on etstem and show others. All right, questions about this program, how this works? So it's one sequential program, but it's as if it's run twice. And the PID is different in those two executions. This PID program value is different in these executions. So one program will go here, another program will go here. Yeah.
So the child's PID becomes 0, right?
Becomes the child's becomes 0. Yeah.
If you pull that child again, you would have like a new, will it have its child's PID and then that child would have.
Yeah, so this was the nested fork question. All right, so let's do this. Let's do another fork here. So I'm just going to copy this code, and I'm going to I'll just put it here. All right, so let's call fork again, and I'm just going to, for like, I don't know, sanity's sake, I'll use a different child PID, which is the variable PID2, inside child's child process. So I've done this program here where I start with one program, call fork, so now we have two processes, and then in the child, I call fork again to make another process, giving us 3 processes total. Oops. So so I know this is getting more complicated, but what should be printed out by this program? Let's see if we can fit the whole thing in here. So we call fork, and then if we're in the parent, we just print out the child's PID here. So this will print PID in the parent. But if we're in the child, we call fork again. And if we're in the parent, that is the child that we created, so we call fork again. So this child becomes this child becomes a parent. And it prints out PID2. And then the child's child prints out, inside child's process. And actually, at the beginning of the fork, we also called inside child process. So we should see, what we should see printed out is child PID here. That's this print. We should see this print statement here. Then we should see inside child process and also child PID. All right, let's just run it. Let's see it, since I think this is getting a little complicated. Let me actually save this. Oops. Okay, so we had that sleep for 5 at the beginning. So let me pause it here so you can see. I think I forgot to quit a previous fork. We're getting a lot of forks here. Let me run this again. So we got one fork. Now we've got 3 forks, which is what we expect, right? We have 3 programs running. And here is all we expected to see. So we saw these, let me do it this way. So here's all of our forks, here's all of our print statements, 1, 2, 3, 4. There's our 4 print statements. And here are the 4 outputs from those print statements. Questions on this? I know this is a little bit more complicated than I was intending to show, but I got several questions. But you can just see that it works like this diagram, where we have just a new program being run. If you call fork again, you're going to get another process from that. However many times you call fork, you're going to get the process. If both the parent and the child called fork, you'd have 2 more processes being created, like a binary tree. Questions on this? Yeah. I think so. Yeah, I think there's probably a system call for it. I think there's probably a sys call for that. I don't know what it is though.
I'm assuming they probably have a way, they implemented a way for child.
Where a child what?
Or a child can have its parent process completely.
Yeah, you could get your parent process pre-ID and then kill it. You could do that, yeah. Yeah, you could do that. All right, so I think we've done fork quite a bit. Questions about fork. So this is the more complicated case. Don't worry too much about this if you don't want to wrap your head around this. Let me call this the child fork. And let's get back to fork here. So the main one I want to get across is this version of fork here, where we've got, let me get rid of this sleep here, where we just have one process that we originally created from bash creating a new process. And we use this switch case statement or an if statement to perform different things, have different code for the child and the parent process. It's as if we ran this entire program twice after the fork. Questions on this? Questions on this normal fork? Yeah.
So the child PID always is 0.
Yes, the child PID is always 0. Yeah. This is the kernel interface defined. So that's just so you can test it. You have something to test. I mean, I guess you could you can always get your own PID with this syscall. Okay, so let's look at, and any other questions? Other questions on this fork? So that's just fork. We haven't even run a new program. It's the same program being run. So you can see why this is separated from exec, because you could just do parallel programming here with just fork. You could create new processes and have in one program write concurrent code that runs in parallel with fork. Okay, let's look at exec. So exec is, actually compared to fork, it's probably a little simpler to think about. Oops, that's the compile program. So let's look at simple exec. Let's take a look at the man page. So there's a whole bunch of variations of exec, and read the Linux programming interface if you want to learn about all these different variations. It's just what gets passed to it and the format of the arguments. But we're going to use this one, exec VE. Actually, we might use a different variation for the project, an easier one. But I'm going to use this for the illustration. So for now, all you really need to know about is the program name. So you give a program name here, and then you give argv. So this is where argv comes from, like the arguments to the main. This is where it comes from. It comes from the exec syscall. They get passed through the system to your program, and then the environment, that's the stuff like path and home, those other environment variables I told you about. Don't worry about that here. We're not going to use that in this class. Read the Linux programming interface for more information about that. All right, so we call exec v, and what exec v does, let's look at its return values. On success, exec ve does not return. So if there's no error, exec ve just will not return. So if exec ve is successful, will this be printed out? Will p error be reached? No, it won't be reached because exec ve just will never return. Instead, what happens? Exec ve loads in whatever program we gave it and just starts running it from the beginning. It overwrites the memory of the current process. The current process still exists, including its open files, but the memory is overwritten. So, the stack, the heap, the text segment, the part that holds the program, that's overwritten. And then instead that program runs. So let me add a little code here to show you what happens in this program. And then even though we have the p error, I'll also put after exec here. Okay, so what do you think will be executed when I run this program? What do you expect to see when I run this program? What's that? Okay, maybe before and after. Any other takes? So remember, exec doesn't return if it's successful. Yeah. What's that? Anything else? Just before? Anything else to be printed? So remember, it's running another program called hello. Yeah. Well, it would be bash because we're running our own program. So it depends. It depends on whether this hello program exists or not. So remember, it's calling another process by name. So here in this program, I don't have a program called hello right now. I have hello.c, but I don't have a hello program. So I guess so I don't have a hello program. So if I run this, I'm going to get an exec.ve error. So if the process doesn't exist, it'll return -1, and it's because the file doesn't exist. If the hello program does exist, so here's showing you that here's the hello program where I'm running it. The hello program runs hello world. So now that the hello program exists, what should we expect to see in our simple exec program? So, it says prog is hello, it calls before exec, and then exec.ve, remember what exec.ve does, is it replaces this process's memory and doesn't return. It starts executing that program and does not return. So what should we see from simple exec, this program? So will after exec be executed? No, it shouldn't, right? But what should be printed out? Hello world, right? It'll print out whatever hello world prints out. It'll print out whatever hello world prints out. So what happens? It runs before exec, and then exec.ve finds this program. It exists, so it's relative to the current working directory. Finds this program, replaces the memory of the current process, and starts running that program from the beginning. And so none of the code in the rest of this process will execute. It's all dead code. And instead, our new process, like a virus, has just overwritten this current program, literally overwritten the memory of it, and the kernel has restarted its program counter at 0, or whatever the beginning of the program is at main, and started running this program. Questions on that? Is that yeah.
So when you say everything's live,
Yeah.
regarding to this process,
Yeah.
if you were to pass it, say an address of a variable inside this, it wouldn't do anything to this stuff.
It would be different. The data is not guaranteed to be the same anymore. Questions on this? So it's replacing our current process with a new running program. And so the way you check for an error is you just see if there's any code after exec.ve. That could only happen if there's an error. So there's no need to test any return value. I mean, you could, but there's really no need to do it. It'll return -1. You could test it, but the only thing that can happen if it's successful is the rest of your current program doesn't execute. So remember, this is not creating a new process. This is just replacing the current process with a different program. Questions? Questions on exec.ve? This one's a little simpler, right? This one's hopefully a little simpler wrap around it. There's no concurrency here. It's almost as like a function call. You could think of this as a function call to hello worlds, or hello programs main. It's kind of like that, yeah.
So, the thing is, I tried doing this quote. It said, hello, I did a cat.
Mm-hmm. Oh, yeah.
I did a list.
You did ls?
LS, yeah. So, but it
Oh, yeah, okay.
that's because it's not.
It's because it's not in the path.
Okay.
It's not in the path. So I change this to ls, and if I just run, if I rebuild this and run simple exec, I'm going to get an error. So no such file found. So this is what bash does for you. Bash will look up will find the location, the path, the full path of that program. So if I just give the full path here, then it will work. So now I'm running ls. So yeah, you have to give the full path, or you have to give the path to the program. But when we're using bash, what bash does, if I type ls, remember it looks up in this environment variable, it looks up for an ls program in that path. So that's what bash is doing for you. The system calls, or at least this system call doesn't. There is a variation of the system call called exec.vp path, which will do the path lookup for you. Yeah. I think I'll probably have you use that for the shell program, just because it's easier. But yeah, there is a syscall for doing that as well. All right, questions on this? Questions on exec? Okay, so I'll probably review this next time because I can tell this is a lot to digest at once. But let's now combine fork and exec. And I didn't copy this program yet. So let's get fork and exec together. All right, let's step through this slowly. Oops. All right, so we've taken our fork program. Oops. This is our fork and exec. We've taken our fork, kind of our template for fork, where we have two different cases, one for the child, one for the parent. Oh, yeah, go ahead.
So if the exec fails, then it'll keep running the code, right?
It'll keep, yeah, it'll move to the next instruction after exec VE and start running that. Yeah, and run that. So that's the simple exec one. It'll run. That's why we had after exec VE. Bless you. All right, so we combine the two programs now. We've got fork, which, with this case style, we have one branch or one block for the child, one block for the parent. But instead, in the child, we run exec VE. We took that simple exec VE program that I had, and we put it as the child, what the child does. So now, what do you expect? So this program is running ls. Actually, let's make it do hello. So it's like what we had before. What do we expect to see when we run this program? So we have a program that forks, assuming the fork is correct. Inside the parent, we print out the child PID, and inside the child, we try to exec the hello program. So what should be printed out when we run this program? Yeah.
Does hello exist?
Yes, hello exists. Now it exists. Now hello exists.
Then I guess it'll run hello.
It'll run hello.
It's not going to print the error.
It's not going to print the error. Is anything else going to be printed out when I run this program?
It won't return the exit failure.
Won't return. Yeah, none of this code will be written if hello exists. Well, anything else be printed out? Yeah. And child PID. Both the parent and the child will run. So the parent will run, the child will run, but the child, instead of doing what we did before, printing out, it will execute the hello program. So we should see whatever the hello program runs and this print statement from the parent. Yeah. No, it's just what we showed before where you call fork more time. If you want to do a fork bomb, you would put it in a while loop. So that way, yeah, if you want to do a fork bomb, you could try it on your own machine. So here we go. We've got now, it's a little ugly because of my spacing here. But you can see, here's Hello World, here's the Hello World program, and here's the here's the child PID here. Oh, we also had inside child process. So there's all the print statements here. We've got the Hello World program running, we have inside child process, and we have child PID. And this could be any program. So if I change this to the ls program, then what should I see? I should see, where's the rest of my, so it's here somewhere. So the spacing is a little messed up because of the way the IO is working, but here's child PID inside child process. That's the parent and the child, and here's the output of the ls program that I ran. Yeah.
When you start a new program, it automatically puts the output in the new terminal?
No, so remember what happens when you fork the process, it copies all of the open files, including standard IO. So without doing anything else, we'll talk about this next time, without doing anything else, both processes will have the same output and input. It'll have all the same open files. So that's why you see everything being written to Bash's output. And also because I didn't wait for the child process, Bash also started running again. That's why you see Bash's prompt here. So the parent exited and Bash is running again. So Bash put its prompt. I could avoid that by putting wait, but I'll I'll show this next time, but you can see that we've got bash running, we've got user bin ls running, and we have the parent running all at the same time. Let me put a sleep in here to make this a little less ugly to look at. And we can see okay, so there's the parent process. And we can see right now we've got two copies of the fork exec program running. The parent process already printed out its code. And if I resume, then the parent process is going to exit, and ls is going to run. So here's ls running. It slept for 10 seconds and then ran. And actually, if I put I'd have to have a long-running program to show this, but if I called a long-running program, you would see that the ls process, this process is now ls instead of fork, because I've ran the ls process. Anyway, questions on fork and exec together? Yeah. Yeah. Oh yeah. It'll replace the fork process with the ls program. So I could do find, which is a really long running thing, and hopefully show. This output is going to be a little ugly. So it's so right now it's 2 versions of fork exec, and find is going to start running soon. Oh, it just ran in my current process, or my current what happened? I think it ran in my current, sorry, I hadn't worked this out. I need to run some long running program to make this, to show you that the name of the process changes. But I'm basically out of time. Let me, okay, there it's running. So the problem is it's running in the background and you can't see the process. But anyway, I'll set up something better for next time so you can actually see the name of the process running. All right, so homework is up. I'll see you all next time.